Hello, and welcome to your lesson for Thursday, December 7th. Today we're going to be working on two new types of reactions. We're going to work with combustion and single replacement. So here we go. We're going to jump right in. Your first assignment is going to be doing a comic strip. So you're actually going to pause this and work on this activity before you move forward. This is due before you leave class today. So you're going to be doing a comic strip for each reaction type. It can't be an example that I just have written on here. It needs to be your own. And so I want you to get creative. I want you to think of some things that would mimic what we've been doing with these types of reactions. When you're done, you're going to take a screenshot or a picture of your image on your paper. You'll just take one picture of the whole page and upload that into the assignment for Canvas. This is a grade today and it needs to be done before you leave class. You should only take about 10 minutes on this. Don't take too long. So go ahead and pause the video here and start on this if you haven't done it already. We're not going to use the timer. We're going to move forward. So here's some examples of what I have on mine that I just found online that you guys can use. Just, don't get crazy. It doesn't have to be wild. Just something that indicates the same idea of what these 5 different types of reaction represent for us. Okay. All right, so the first thing we're going to do is we're going to talk about combustion. Combustion is a reaction where oxygen is specifically involved. I'm going to make sure my pen is working. There we go. Oxygen is our element that we are most interested in. And remember, oxygen, when it is in its elemental form, is diatomic, so it's always an O2. So O2 is going to be in the reactant side of every combustion reaction that we use. This will always be a massive release of energy in the form of heat and or light. And typically this means an explosion or a boom for us. Whoops, let me back up. Or some sort of, it could be a bomb. I wasn't trying to write bomb, but it could be some sort of an explosion that's going to cause lots of heat and lots of energy to be released. It can combine in lots of different substances, and so they're very common reactions. As you can see here, we have hydrogen reacting with oxygen to make water, okay? And so you can see we've got 2 hydrogens with 1 oxygen, and that makes water. And so you probably recognize from yesterday's lesson that this is actually a synthesis reaction, but it's also a combustion. And so it's categorized twice because of the reactant of oxygen present, okay? We can see that carbon and oxygen can combine to form carbon dioxide. We can see that methane, which is called a hydrocarbon because it's made of hydrogen and carbon. A hydrocarbon of methane, which is the simplest version of a hydrocarbon we can have, can be reacting with our oxygen, and this makes carbon dioxide and water. And we're going to talk more about that here in just a bit. All right, so what I'm going to do next is we're going to talk a little bit about combustion that happens in the movies. I know that it gets used quite a bit in action-packed movies. I'm actually going to show you a clip of a combustion situation in a pretty famous movie, and so we're going to pause real quickly and we're going to go watch this movie just for a few minutes. So let's go ahead and watch together.
Surprise. I did not die on Sol 18. If the oxygenator breaks, I'm gonna suffocate. If the water reclaimer breaks, I'll die of thirst. If the hab breaches, I'm just gonna kind of implode. And if by some miracle none of that happens, eventually I'm gonna run out of food. I'm not gonna die here. Our service mission here was supposed to last 31 souls. For redundancy, they sent 68 souls worth of food. That's for 6 people. So for just me, that's gonna last 300 souls, which I figure I can stretch to 400 if I ration. So I gotta figure out a way to grow 3 years worth of food here on a planet where nothing grows. Luckily, I'm a botanist. The problem is water. I have created 126 square meters of soil, but every cubic meter of soil requires 40 liters of water to be farmable. So I gotta make a lot more water. Good thing is I know the recipe. You take hydrogen, you add oxygen, you burn. Now I have hundreds of liters of unused hydrazine at the NDB. If I run the hydrazine over an iridium catalyst, it'll separate into N2 and H2. And then if I just direct the hydrogen into a small area and burn it. Luckily, in the history of humanity, nothing bad has ever happened from lighting hydrogen on fire. NASA hates fire because of the whole fire makes everybody die in space thing. It's been 48 sols since I planted the potatoes, so now it's time to reap and re-sow. They grew even better than I expected. I now have 400 healthy potato plants. I dug them up, being careful to leave their plants alive. The smaller ones I'll reseed. The larger ones are my food supply. All natural, organic, Martian-grown potatoes. You don't hear that every day, do you?
All right, so we're going to talk a little bit about what he did there and what reactions he utilized to help him survive on Mars. So he used a chemical called hydrazine, which is N2H4. He said that he broke it down. Well, you guys learned yesterday that this is just a decomposition reaction. He did use a catalyst, that iridium, but it's not part of the actual reaction whenever we do our decompositions. So when we break it apart, I'm going to put nitrogen by itself, and I'm going to put hydrogen by itself. But we also know that nitrogen and hydrogen are part of our diatomics, and so we're going to double those. All right, and then all we have to do is balance from there. So I'll put a 2 in front of hydrogen. And so this is the original reaction he used. Now hydrazine is actually a rocket propellant. And that's where he got it from. He got it from the rocket. And so he utilized this hydrogen here to be able to go make some more water. So he said he had some H2 and there was oxygen in the room. And he lit it on fire and he made those water molecules that you saw sticking to the sides of that plastic wall that he had created. So we'll go ahead and balance this one also. I have 2 hydrogens, 2 hydrogens, 2 oxygens, and just 1 oxygen. So over here on the right, I'll double this, which means I'm going to double this. So he took this hydrogen and he used it to create water. Now, this is called a combustion reaction because of the presence of that oxygen there in the reactant side. So I just wanted to show you guys a cool way that Hollywood has used chemistry in their storyline. Obviously, we don't have life on Mars, but it was kind of a cool story. Now, the majority of the combustion reactions that we're actually going to be working with are going to involve the hydrocarbons. And I want to show you one of them in particular that you guys should be familiar with. Whoops, wrong one. Hold on, let me back up. Let me erase that 6, or that 2. It needed to be a 6. Okay, if you guys know what this chemical is, you probably remember it from your biology class. This is glucose. And so you guys learned in biology that if you take glucose and you react it with the oxygen in your body, you can make carbon dioxide that you release and you produce water as well. Well, this is a combustion reaction. All right, and this is the combustion reaction that literally keeps our body running the way it is. But here's a question that I have for you. Why don't our bodies blow up if we are literally having combustion reactions happening in every cell at every moment of our life? Well, if you will recall, whenever you guys were doing your biology class, the production or the breakdown of glucose is in multiple steps. We take that glucose and we put it through glycolysis to break it down, and then we take those molecules and we go through the Krebs cycle, and then we went through the electron transport chain. So there was a whole process to breaking down that glucose molecule, and the overall reaction was this one, but there was many reactions that happened in the middle from the beginning to the end to keep those particles from blowing up in your body. And so it's pretty spectacular how our bodies are able to use something that we could potentially blow up from, but that we have harnessed that energy in a very efficient way. All right, so back to the combustion. There's a couple of things. I know my class in particular has already seen this, but I want to make sure we all know that when you do balance a combustion reaction that has hydrocarbons in it, you always want to balance them in the order of your elements showing up. And that will be carbon and then hydrogen and then oxygen. We actually like to save that little O2 molecule from the reactants as the absolute last piece. Okay, that's usually the thing that's going to fix everything at the end. So when we're writing our combustion reactions, a couple of things for predicting our products, that we do have a diatomic element involved. We have our oxygen. The great thing, the really cool thing is that there's literally the same product every single time that we work these questions if it's a hydrocarbon starting the process, okay? And I'll show you what that means here in just a minute, because remember, that carbon-based compound, it's going to be C something, H something, okay? That's what we're talking about. Or it could also look like C something, H something, and sometimes it even has an O in it, and that's okay. It does not matter what those carbon-based compounds look like. As long as they have carbon and hydrogen in them, they are going to produce these same products every single time. So combustion actually, in my opinion, turns into the easiest one to do because you already know what the products are. So we're going to go ahead and we're going to move forward and work one of those. So this very first example says isopropyl alcohol. We have C3H8O, reacts with oxygen in the air. Okay, and when it's lit, it produces carbon dioxide and water. So isopropyl alcohol, this would be my reactant 1. Reacts with means a plus sign. Oxygen in the air, there's my second reactant. That is my indicator that this is a combustion reaction. When lit, to produce. Okay, so to produce is my arrow. That's my yield sign. Okay, carbon dioxide, there's product number 1, and plus sign, water, product number 2. So this is going to be pretty easy to throw down. Let's go ahead and get started. We're going to have C3H8O plus oxygen. Remember, oxygen is O2. Yields CO2 plus H2O. Now, it doesn't matter what order you put these in. You could have put water first or carbon dioxide first. It does not matter as long as they're on the product side. So there's my skeleton equation, and then we always have to balance. And so remember, when we're balancing, we want to go carbon, then hydrogen, then oxygen. It just makes it easier, okay? So I'm going to go ahead and get started with this, and I want you to remember, when we're doing our balancing, it's always best practice to do this in pencil because there's always opportunities to have to erase things. So don't be afraid to, work in pencil and erase when you need to, because sometimes we start a process and then we have to kind of backtrack a little bit. So, all right, carbon first. So carbon has 3 here, so I'm going to put a 3 here. Hydrogen is an 8. So, whoops, nope, I already messed that up. Give me a second. That's supposed to be a 4 because we have to divide by 2. Let's do that again. Okay, so there's my 4. Remember, a coefficient is always going to follow everybody behind it. So this 3 applies to carbon and it applies to the oxygen. Okay, so this is telling me there's 6 oxygens on this one and 4 oxygens here. So this is a total of 10 on the right. Now, this isopropyl alcohol has an oxygen on the actual hydrocarbon, which actually creates an odd number for me. And if you will recall, my students in particular, anytime you end up with an odd number of something on the left and an even number on the right, we have to get rid of that odd. The way that we're going to do that is we're going to double the odd, and the odd came from the hydrocarbon. So I'm actually going to double this. And then we're going to start over, and it should work out just fine for us. So 2 times 3 is 6 carbons, so I'm going to make a 6 for carbon. 2 times 8 is 16 hydrogens total, so I need an 8 over here. I think I had gotten ahead of myself earlier, so that gives me 16 hydrogens. All right, so we're going to count our oxygens very carefully. 6 times 2 is 12 plus 8 more, so this is a total of 20 oxygens on the right. Now over here on the left, I have 2 plus something has to equal 20. Okay, because the law of conservation of matter says that everything has to be balanced. This total here has to be 18. So 18 divided by 2 would give me a 9. And so that would be my final reaction. Everything ready to go, balanced and good for us to move on. If you need to pause and rewind that and watch me again, feel free to do so, but we are going to do some more examples. Next, we're going to look at methane. And anytime they say combustion, it literally tells you everything you need to know. All right, so here's our hydrocarbon, CH4. And the fact that they say combust, hold on. I didn't mean to, it looked like I crossed it out. Try that again. And we're going to try this one more time. H4, much better. Anytime we say that it's going to combust, that means plus oxygen, right? What we just learned is that the word combustion means it has to interact with oxygen. So we're going to add our O2. And then because we know it's a combustion with a hydrocarbon, I already know my products. I know that it's going to be carbon dioxide, and I know that it's going to be water. Okay, this will not change. It does not matter what hydrocarbon we're working with. So once I have all my pieces, now I'm going to start to balance one carbon, 4 hydrogens, 2 hydrogens, so I need a 2 in front. 2 times 2 is 4 now. And then remember, I've got oxygen on both of my products, so we've got to be very careful when we read these. The oxygen is the hardest part, the thing that we kind of mess up the most often, so just be very careful. 2 oxygens here and 2 oxygens here, so it's a total of 4 on the right-hand side. And that means I need a 2 on the O2 to be able to balance the whole thing. And that one's all done. And states of matter. So here's the really great thing about states of matter. Did it keep my stuff? It sure did. Everything in a combustion reaction gets to be a gas. Once again, I find these to be literally the easiest ones we work. So you get a gas, and you get a gas. You get gas, you get gas. And the reason why the water is a gas, because this is really hot. As you guys saw in the very first slide, we're producing heat and light, so there's energy involved here, but it's not a particle, so we're not putting it in the reaction. But there's always energy going on. And so it's always hotter than water's boiling point, so it's always going to be in a gas phase whenever we're working through these, okay? All right, here's a couple more. I want you to try these out. At least give me the skeleton equation minimum, but I'd love for you to try to balance them yourself without my help. And then I'm going to join you and we'll check your work. Okay, so go ahead and pause me and try these on your own, and then we'll start it up together. Okay, so let's go ahead and jump in. C2. H6O2, that's called ethanoic acid, is burned in air. So anytime burned in air, burned in oxygen, combust, these are all different ways that they say, we're reacting with oxygen, okay? And because it's a hydrocarbon, we're going to produce those same 2 products. Oops. My eraser takes longer than I want, but that's okay. H2O. Okay, so now we're going to balance. So 2 carbons, 2 carbons, 6 hydrogens, so I'm going to put a 3 here. All right, so I've got an even number of oxygens on the left, and I've got an odd number of oxygens on the right. So see how this is 4 here, plus 7, or plus 3 makes 7. Anytime we're getting our odd number that we're not going to be able to counterbalance, we're going to pause the work, and we're going to double where the odd came from. So the odd came from hydrogen because of the 6. So I'm going to double my hydrocarbon, and we're going to start again. Okay. Anytime you end up with an odd on the left and an even on the right, we're going to double the odd. It's the easiest way to remove that piece. So 2 more for carbon, so that's a 4 total. Now we're up to 12 hydrogens, so we're going to put a 6. 4 times 2 makes 8 oxygens and 6 more. That's a total of 14. Now, be very careful because now we have these oxygens here that we have to subtract. So the whole thing has to equal 14 still. We have some amount that's going to have to be with this O2, but right now we've got 4 on the hydrocarbon. Okay, the oxygen is the trickiest part, especially on ones like this because they're in everything in the reaction. So just be very careful. So we should end up with 10 needed for this one here, which means I need a 5 on the coefficient. All right, so then we're going to go ahead and do propane. Once again, if you haven't done it yet, pause it, try it, and then come join me and we'll check your work. C3H8 plus O2, burned in air. means plus O2, right? We're going to make the same products, CO2 and water. Okay, 3 carbons, 3 carbons, 8 hydrogens. So I need 8 total. Whoops. I need to make a 4. All right, so I'm at 6 oxygens plus 4 more would be 10 total on the reactant side, which means I need a 5 on the reactant side. Oh, and I forgot again. Everything gets gas. There we go. Okay, there's our examples for those. So I actually want to pull up this Darvaza crater that we talked with you about at the very beginning of this unit. So on Monday, we showed you a couple of videos about the Darvaza crater. So now that we've learned a little bit more about reactions and we see that there is a burning happening, what do you think is the source as far as type of reaction going on here? Hopefully you're noticing that this would be a combustion reaction happening. And so you could maybe put a generic formula down as to what that reaction might look like. Okay, and we gave you a couple of extras. So I think you have a little box on your paper just to jot down a couple of thoughts, but this is another little opportunity for us to remember what we started with, okay? And we're gonna keep giving you little hints as we go. Okay, so that was combustion. Now we're going to move into single replacement, and after we finish single replacement, we will be done for the day. Apparently my stuff did not transfer well when I converted it, so sorry, that should be an arrow. A single replacement reaction is one where the atoms of one element replace the atoms of another element in the compound. And so this would be like, you know, in the examples that you guys did on your card sort, it would be like 2 people are dating and then they break up and somebody else jumps into a new relationship, right? When we're bonding these, our metal will kick out another metal, or a non-metal will kick out another non-metal. Okay, so that's really important. We don't ever have a metal kick out another non-metal, or vice versa. So notice here in this example, zinc and copper are my 2 metals, and they're the ones that are going to be trading places. Okay. In the examples that we were looking at on our card sorts, if a guy was the single one on there, then he was replacing the other guy. If there was a girl on the single card, part of the card, then she was replacing another girl. So in that thought, they're going to replace the thing that they're like, okay? And that's how we're going to kind of think about that. So here we go. We're going to get into some bigger definitions of this. So metal replaces hydrogen. The reason why it can replace hydrogen, this would be my only exception, is that hydrogen is a positively charged nonmetal. If I have a highly reactive metal, it can replace hydrogen in a compound, such as water. And so we would, come on, pen. We would have to have a compound, this is an error, whoops, hold on, let me go back. We would have to have a compound that can be soluble in water, and remember for the solubility, we had that solubility chart. So you can reference that. But metal plus water makes a metal hydroxide. So it's not going to kick out every hydrogen. It's going to kick out one. Okay. So this product comes from kicking out, oops, apparently I can't spell today either. It's been a long day. Sorry, guys. Lots of training. It's going to kick out one hydrogen and keep the other to make the hydroxide, okay? So we'll have our metal hydroxide plus hydrogen gas. Hydrogen gas is diatomic, just like normal. So here we would have sodium reacting with water, making sodium hydroxide plus hydrogen. Whereas if I have metals that are less reactive, so for example, if I have iron trying to react with water, it's a less reactive metal, so it's going to actually be an opportunity for no reaction. And this is the first time you guys have ever seen an opportunity for there to actually be no reaction. This is important because we pick metals for construction. We pick metals for jewelry and things like that that do not react with water because we don't want them to completely dissolve or react. And our jewelry or the structural integrity of our buildings and our bridges and things like that to be put at risk. So we actually want these to be a no reaction, but the reason why they're no reaction is because iron 2 hydroxide would be insoluble in water, or iron 3, either one of those. They would be insoluble, so that's why it's not going to. And we'll take a look at some more things about this here in just a bit. Metals can replace other metals, okay? But not every metal can replace the other metal. This is dependent on their reactivity. The less reactive metal cannot replace the more reactive metal. Okay, so this is super important for us right here. Okay, so for example, that's an arrow. Copper is trying to replace silver here. So copper and silver are trying to swap places. And it is successful, as you can see on the product side. Whereas if silver is trying to replace copper here, it's actually a no reaction. So one will replace the other, but the other can't replace the original. And so it's kind of like if you're in a relationship with someone and they, everything is fine. And then somebody else comes up to you and is like, hey, you should ditch your boyfriend or girlfriend and you should start dating me. Well, if you don't think that person is worthy of kicking out, right? They're not as bigger, buffer, stronger, funnier, whatever reason you're with your significant other, then you'd be like, yeah, no, I'm good. I'm good with this one. I'm good with this relationship, and that you would have them move on, right? It's the same kind of idea. The metals have their own little way of deciding who gets to, kick out who. And we're about to talk about that here in just a second. It's called the reactivity or the activity series that we're going to look at. Our last possibility before we look into our activity series is our non-metal. So those can react as well together. They can kick each other out. And this is typically going to be our halogens. Those are really the only ones that we're going to focus on in your class. So the reactivity of your halogens is exhibited by different levels in single replacement reactions as well. The more reactive halogen is higher than a less reactive halogen within the compound. So here we have fluorine trying to kick out bromine. Okay, so notice it's the non-metal trying to kick the non-metal, right? And then, so fluorine can kick bromine out, and the reaction can occur, but bromine cannot kick fluorine out. See, bromine is trying to kick fluorine here, not sodium. And actually, the way that they're organized is they are already grouped on the periodic table correctly. So we have fluorine. Oh man, I should know this. It's late. Let me pull up my periodic table. Chlorine, yeah, I thought so. Fluorine, bromine, iodine. Okay, those are really the ones that we're looking at. They're actually already in order. So fluorine is the most active, and it can kick out anybody below it. And iodine is the least active, and it can't kick anybody out. Okay, so most active, fluorine. Fluorine can kick out chlorine, it can kick out bromine, it can kick out iodine. Chlorine can kick out bromine or iodine, not fluorine. Bromine can kick out iodine, but not chlorine or fluorine. And iodine can't kick out anybody, unfortunately. And so hopefully that makes sense. We're going to keep working on some. So we'll get some more examples on that. But it's all about their activity. Here is that list that you guys, or that I was referencing. So this is not a list you will memorize. This is a list you will reference. Okay, I will always give it to you. And so here we have decreasing activity. Oh, these should be flip-flopped. Sorry, switch those on your paper. Decreasing activity. So this is the most active up here, and the least active down here. This is in general, a metal can displace or replace. Another word for replace, any of the metals that are lower than them. Same rule applies for the halogens. So lithium can be an element by itself and replace anybody on here into the compound. Typically we see the group 1 and group 2 metals kind of appear at the top. Then we'll start to see our transition metals. And then hydrogen is here. And then these down here at the bottom are all of our jewelry metals. We don't want our jewelry metals to replace things because that means that the solid, when we put them into different chemicals, could react and then your jewelry falls apart. So we don't want to mess up the structural integrity of our jewelry, which is why we pick these metals, because they're at the bottom of the list. They're the least reactive. They're the most stable metals. They're not going to participate in the bonding, okay? So here you guys can see we have a container of copper sulfate, and we stick a piece of iron in a nail. The copper will actually start coming out of the solution, and it will start to solidify. That's what that orange is. That's actually copper collecting on the nail. And see how copper sulfate is typically blue? It gets less blue because now we have iron inside of it. That would just be a visual example there, but I'm actually about to do this PhET simulation here, and I'm going to show you a couple more things. There we go. All right, so here is a particle diagram of what's happening. Here we have copper, piece of metal. So here's the metal in the liquid. The liquid is a solution of silver. Okay, so this reaction would be copper plus silver, something maybe like a silver nitrate. Okay, and we want to see, can the copper kick the silver out of the solution and replace it to make the silver now the solid. Okay, so that's what we're going to look at, and we're going to run this. So go ahead and watch with me. Oh, did you see that swap? Oh, there's another one. So the fact that there is a swap happening, notice that the copper was not charged, and then when it went into the liquid, it's now charged, and silver wasn't charged, and now it's a solid, and it's not charged anymore. Do you guys see that? So that's indicating that copper and silver are literally trading places. Silver now becomes the solid, and copper now goes into the liquid. All right, we're going to do some more of this, okay? I want this to really stick in your head. Okay, so here, let's go ahead and we'll do, I'm going to pause the run. We're going to do potassium and silver. Let's see if silver can replace potassium. potassium can replace silver, my bad. Notice this is another one where potassium is higher on the list, so it can kick silver out of the liquid, out of the compound, and into a solid phase by itself. Let me flip this. Let me go sodium versus zinc. All right, so this would be zinc trying to replace sodium. And notice the sodium's just breeze right past it, right? So there's no way that the sodium is going to go be a solid and be replaced by the zinc. So the sodium's like, nah, you're not going to steal my girlfriend. I'm good. I'm better than you. You're not going to replace me, right? If you want to go with that example, we can look at gold. Look at that. Gold's not going to be replacing anyone. Gold's going to stay a solid, right? We can go platinum versus gold. There we go. I'll let you watch one more and then we're going to switch over. This video is already long enough. Let's go. There it is. So here we can have gold plating off of the platinum. Now the platinum is in the solution, okay? All right, so that's just a little example of kind of what's going on the particle level. I know sometimes it can be really hard to see what's going on, so I wanted to show you guys that. So here we have a couple of reactions we're going to do, and then we're going to get out of here. So it says solid zinc, okay, so solid, they're telling us our state of matter, reacts with, there's my plus sign, silver nitrate to produce arrow, silver plus zinc nitrate, like that, okay? So we're going to write our skeleton out. So zinc, solid, reacts with plus silver nitrate. Silver is Ag with a +1. Nitrate, NO3, -1. They're 1 to 1, so we're just going to write them out, AgNO3. And if I don't have my solubility chart with me, but you can turn the page and you can see that nitrates are always aqueous. All right, we're going to produce silver, Ag, solid, and zinc nitrate, Zn. Remember, zinc is a +2, nitrate's still a -1, didn't change. So I actually need two of those this time. Now, before we move forward, we're actually going to back up for a minute. We're going to look at that activity series. Oh, yeah. And I want you to look. Okay, so right now, I'm trying to have zinc kick out silver. Zinc is higher than silver, so this reaction can happen, so we can proceed. All right, so we just want to check them, because if it's no reaction, you don't want to do extra work than you have to. 1 zinc, 1 zinc, 1 silver, 1 silver. Okay, so far so good. 1 nitrate and 2 nitrates, so we're actually going to double this up, and therefore I'm going to double. I don't know why I wrote that 3. Let's try that again. 2. There we go. And it's all done. Let's try another one. Bromine reacts with calcium iodide to form iodine and calcium bromide. All right. We know that bromine is a diatomic molecule, so we're going to write it as Br2 plus calcium iodide. Calcium is a +2 and iodine is a -1. So we're going to swap and drop. That's an A. To form iodine, I2, it's diatomic. Not because I had 2 of them over there. Remember, we don't care how many are over there. It's because it's diatomic. And calcium bromide. Bromine's a -1 also, so it's going to look very similar. Similar chemical behavior. There we go. All right. And then states of matter are bromine, if you'll remember from my big periodic table, is blue, so it's a liquid. Calcium iodide is going to be aqueous. Don't do that. Aqueous. Iodine is actually a solid. And calcium bromide would be aqueous also, I believe. And it's actually already balanced. Sometimes we get lucky and we don't have to do extra work. Now, the last thing we do, I forgot to do this beforehand. We need to see, can bromine kick out iodine? And it is higher on the list, so it is a yes. Okay, and that's all we have for today. You guys should be on, let me think, 13, 14, I think we're on 16 today. So you guys should be doing page 16 for your homework. That should give you your examples of these types of questions. Where's my mouse? Come on, there it is. And please feel free to reach out to Mr. Shanzer or I to get you guys some help. Thanks. Bye.